Have you ever stopped and wondered how scientists can be so sure about the shape of a molecule they've just made? I mean, we're talking about things that are completely, totally invisible. Well, it turns out they use this incredible technique that pretty much lets them listen to the atoms themselves. So let's tune in and find out how it all works.
Okay, so let's put ourselves in a chemist's shoes for a minute. You spend weeks, maybe months in the lab, mixing things, heating things, trying to create a brand new molecule. You finally get a little vial of something. You hope it's trillions and trillions of your new molecule. But how do you know? How can you possibly prove it and map out its exact 3D structure when you can't see a single one?
Well, this is where the real detective work begins. Figuring out a molecule's structure is just like solving a microscopic mystery. And the #1 tool for cracking the case is something called nuclear magnetic resonance spectroscopy. Yeah, it's a mouthful, so we just call it NMR.
And you really need to solve that mystery, because without knowing its structure, a new chemical is basically just a blob. You have no idea what its properties are, what it can do, or how it might react with anything else. You absolutely need a reliable blueprint of how every single atom is arranged.
And this is where it gets really brilliant. Instead of trying to look at the molecule, which is impossible, NMR lets us listen to it. Seriously, it picks up these tiny radio signals that are being broadcast from the very heart of the atoms, from the nucleus, and those signals give us all the clues we need to piece the whole puzzle together.
So how on earth does that work? How do you listen to an atom? Well, it all comes down to some really clever physics that involves tiny, tiny magnets and radio waves. You can think of it like a finely tuned subatomic level puzzle.
The key concept here is something called nuclear spin. It turns out that certain atomic nuclei, and the proton in a hydrogen atom is a perfect example, they have this property called spin. And this spin makes them act like microscopic, spinning compass needles. Each one generates its own little magnetic field.
So, what do you think happens when you take all these tiny compass needles and you stick them inside a giant, super powerful magnetic field? Well, they snap into alignment. They have two choices. They can either line up with the big field, which is a comfy, low-energy state, or they can be forced to line up against it in a more tense, high-energy state. So the whole process is kind of like a four-step dance. First, that giant magnet gets all those little nuclear spins to line up. Then, step 2, we blast the sample with a quick pulse of radio waves. This gives them a kick of energy and flips them into that high-energy state. Third, they don't stay there for long. They relax back down to the low-energy state, and as they do, they give off their own faint radio signals. And finally, a computer listens for those signals and translates them into the spectrum that we, the detectives, get to analyze.
And that spectrum, that's our treasure map. It looks like a bunch of peaks on a graph, but it's actually filled with clues. Every little detail of those peaks tells us something specific about the molecule's structure. If we can decode these clues, we can solve the puzzle.
Okay, so the very first, most basic clue we get is just by counting how many different signals we see. So what does a simple count tell us?
It tells us exactly how many different kinds of hydrogen atoms are in that molecule. See, if a molecule is really symmetrical, a bunch of its hydrogens might be in identical chemical environments. And if they are, they'll all sing at the same frequency. They'll show up as one signal. But if they're in different spots with different atoms around them, they're considered non-equivalent, and each unique type will give us its own separate signal. All right, on to clue number 2. This is the position of each signal on the graph. It's where it shows up along that horizontal axis. We call this the chemical shift. Now this part is super clever. The electrons that are buzzing around each nucleus create their own little magnetic field, which actually shields the nucleus from the big magnet we're using. So, if a proton is sitting next to something that pulls electrons away, like an oxygen atom, it has less shielding and its signal shows up further down the graph. We call that downfield. But if it's in an area with lots of electrons, it's more shielded, and its signal is upfield. So basically, a signal's location tells us all about its local electronic neighborhood. And now, for our final and maybe the most powerful clue of all, spin-spin splitting. This is the phenomenon that turns what would be single sharp peaks into these beautiful complex patterns, doublets, triplets, quartets, you name it.
So what's going on here? Well, the protons can actually feel the tiny magnetic fields of their neighbors on the very next atom. This interaction causes their signal to split, and it follows this really simple, really elegant rule, the n+1 rule. If a proton has n neighbors on the adjacent carbon, its signal gets split into n+1 peaks. This is the magic clue that tells us exactly which pieces of the puzzle are connected to each other.
Okay, theory time is over. Let's put our new detective skills to the test. We're going to use these 3 clues, number of signals, chemical shift, and splitting, to solve the structure of a molecule you've definitely heard of, ethanol.
Let's just pretend for a second that we've been given this spectrum, but we have no idea what the molecule is. All we know is its formula is C2H6O. We look at the spectrum and we see 3 distinct signals. Boom. Clue number 1. There are 3 unique, non-equivalent types of hydrogens in our mystery molecule.
Now let's look at the splitting. This is the good part. There's a signal for a CH3 group, and it's split into a triplet, 3 peaks. Using our n+1 rule, that means it must have 2 neighbors. Let's look at the CH2 group. Its signal is a quartet, 4 peaks. That means it must have 3 neighbors. Do you see it? The CH3 group is next to the CH2 group, and the CH2 group is next to the CH3 group. They perfectly confirm each other's existence. And that last proton, the one on the OH, it's just a single peak, a singlet, because it's kind of on its own.
So when you combine everything, the 3 signals, their positions telling us who's next to the oxygen, and that beautiful splitting pattern revealing the exact connectivity, we can say with 100% confidence that our mystery molecule is ethanol. The evidence is undeniable. Case closed.
But the power of NMR doesn't just stop with figuring out the structure of little molecules in a lab. In fact, its fundamental principles have been scaled way, way up to create one of the most important tools in all of modern medicine.
Now first, it's good to know that NMR isn't just for hydrogen. We can also tune the machine to listen for signals from carbon-13 atoms, and this gives us a totally different perspective. If the proton NMR shows us the skin of the molecule, you can think of carbon-13 NMR as showing us the skeleton, the underlying carbon framework. Together, they give us a complete picture.
This technology is amazing for seeing a complete picture of a molecule. But let's ask a crazy question. What happens if we try to apply these exact same principles, but on a much, much bigger scale? What if our sample wasn't a tiny vial of chemicals, but an entire person?
Well, that is exactly what an MRI is, magnetic resonance imaging. It's just NMR on a human scale. Instead of using the signals to figure out the chemical environment, an MRI machine applies a gradient to the magnetic field. This tweak makes the frequency of a proton signal tell you its physical location in the body. So by decoding all those frequencies, a computer can build a stunningly detailed 3D image of your organs and tissues, all using the same basic physics and with 0 harmful radiation.
It's pretty incredible when you think about it. From the exact blueprint of a single, invisible molecule to a detailed map of the human brain, magnetic resonance has given us this amazing window into worlds we could never see with our eyes. It really makes you wonder, what other invisible worlds are out there, just waiting for us to tune in and listen?